Hello, everybody, and welcome to Engineering Symbiosis AD's 5th lecture video. My name is Nathaniel M. Zaplater. If you had watched my last lecture video, if you had watched my last video posting I made last month, I had said I was going to make a video lecture in response to the Strait of Hormuz energy crisis and the resulting energy shock from the illegal war of aggression waged by the U.S. and Israel on the people of Iran and the closure of the Strait of Hormuz. If you haven't been following the exact economics, roughly more than 20% of global oil has stopped flowing through to East and South Asia, which are the major growing economies in the 21st century, and they're essentially the lifeblood of the global economy because they are where the majority of large-scale manufacturing and shipping to the G7 countries takes place. So like India, China, Vietnam, Thailand, Indonesia, these are all countries where major tech and manufacturing companies, even those in the clean energy and sustainability sectors, and even biomimicry rely on, which is why, like as I predicted in my 11-minute rant video that I made quickly about the U.S. and Israeli war in Iran and the Strait of Hormuz energy crisis, because of the petrol renewable lock-in or paradox, sustainability and specifically biomimicry does not have the ability to fully decouple itself, if at all, from the high-end energy, high extractive energy and production and linear production system of waste that it has grown up in. It is definitely a product of early to middle globalization, especially considering that Janine Benyus's main seminal work, Biomimicry, Inspirations Inspired by Nature, was written in 1997 during the height of globalization. So I really see Symbionics and Urban Ecological Niche Prosthetics, or UENP, as the successor logic that is the byproduct of the end of globalization and a response to the end of globalization. But anyway, this lecture video is going to definitively prove that this Symbionics or Urban Ecological Niche Prosthetics is a superior long-term economic, scientific, and engineering framework to completely get us off of all oil infrastructure and to scale up Symbionics and Urban Ecological Niche Prosthetics to begin the active global ecological restoration and biogeochemical cycle restoration of the planet. Before, if you had studied a lot of clean energy and renewable energy and alternative methods for ecotechnology, you would have been right in identifying the petrol renewable lock-in or paradox as my uncle used to say, there's no way we can get off oil, but even with solar, wind, and tidal power, for example. And my response is yes, you would be correct on that assumption, and a lot of deep ecologists also agree with that, considering basic industry's reliance on things like petrol, like for fertilizer and cheap plastic production. Anyway, this lecture video is proof that I have a method to scale up Symbionics and Urban Ecological Niche Prosthetics in a way that other green and blue technologies, and architectures don't. And this methodology and design are completely roadmapped for me to be able to, and us, because I want to bring other people on board. This is going to be a community and international effort to be able to scale up Symbionics, Urban Ecological Niche Prosthetics, to be fully energy independent and energy sovereign, away from global supply chains, and away from just-in-time production that only serves corporations and corporate consultancy models. But anyway, before I rant on for too long, this is the Strait of Hormuz energy crisis, the petrol renewable paradox, the death of biomimicry, and the S-PBRR, or the Symbiotic Photocatalytic Biofuel Reactor and Refinery. And just to the right here is my first basic AI generated image of my S-PBRR that's based off of my detailed written schematic. I didn't just punch it in and say, design for me a... I didn't just use AI generically and say, design for me a converted oil refinery that could be turned into a biofuel center or biofuel refinery center. If you look at this specific diagram, there's no way that AI could have just generically produced all of these phases, all of these carefully integrated sections without my written schematic. So these are all all these AI images are not what you would call AI slop, quote unquote, because go online right now and look up any sustainable architecture, biomimetic architecture, green tech, blue tech architecture generated by AI that's just generic. And I'm sorry, but mine blows all of that out of the water. And underneath here is something called the zero ecological externality equation, but I won't get into that right now because that's for an entirely different lecture video that will be on my post-scarcity economic theory around biogeochemical cycle restoration and about planning an economy around biogeochemical restoration and planning each economic cycle around the literal biogeochemical and ecological regeneration cycle, and then basically using that as a methodology to create ecological and then material abundance. But that's for an entirely another lecture video. That'll take me a while to make and to fully flesh out. This has taken me long enough, and even still, this lecture video, isn't the absolute best quality that I would have wanted it to be. But I really felt compelled that I needed to get this lecture video recorded and out there, and I just had to power through. And I'm just going to be reading from the slides as best as I can without ranting too much. So here we go. And as my title says, this lecture video and all the invention designs and my equations are all my prior learning in art intellectual property, and all of the designs and equations presented in my lecture videos are my prior learning in art intellectual property. I'm also in the process of getting I am basically already a sole proprietor owner, but I am going to get it officially stamped. So don't think about taking any of my intellectual property without giving me acknowledgement. I'm going to open source it, most of it anyway, once I get recognized for my contribution to science. So anyway, don't rip me off, because I'm going to end up open sourcing it anyway once I get institutionally recognized and scale up. So yeah. Oh, and to the left there is a refinery plant in, I believe, Sarnia or something. So I'm going to keep going before I rant on forever. So what is an S-PBRR anyway? So the Symbionic Photocatalytic Biofuel Reactor and Refinery. The S-PBRR is a macro-scale and iterative phased implementation design strategy for retrofitting and converting any or eventually all stranded, damaged, or otherwise shut down or decommissioned oil refineries and gas processing facilities, or I guess gas processing factories, into biofuel and bioreactor centers for energy production and I also meant to say for energy production and distribution. This is achieved by converting all crude oil and gas/diesel refineries into storage centers for. Sorry, I'm gonna move my recorder because I literally can't see the start of the sentence that I wrote. And gas diesel refineries and storage centers into biofuel and hydrogen fuel production, storage, and maintenance facilities. Powered by biofuel reactors, microbial fuel cells that are in turn, it says created, but I meant to say that are in turn powered by the extra surpluses of glucose, ethanol, and hydrogen fuel cells and microbial fuel cells that used for the final stage of the biofuel polishing in the phase 4 of oil to biofuel conversion strategy through photocatalysis and a combination of natural and artificial photosynthesis. Okay, so I apologize. The image of the photocatalysis reaction is kind of blocking the bottom sentence there of the slide. It's just a basic visual representation of photocatalysis, just to show the audience here. the really awesome and economical thing about photocatalysis is it doesn't, a lot of newer approaches to photocatalytic reactions and even photocatalytic lasers don't require reactive metals that are usually rare metals to spark the react or catalyze the reaction. They literally just use the sun. So that's really awesome. And obviously, this is demonstrating how a semiconductor, a photocatalytic, a photocatalyst, a semiconductor photocatalyst is splitting water into O2 and hydrogen. So anyway, I'm going to continue. I hope you understand that one. So this is phase 1 of S-PBRR, crude and refined oil to biofuel conversion phase. So let me just move my stupid recorder out of the way, or I can't read my own title slide. And of course it's going to do this to the middle of me in recording, but whatever. Just power through. Alright, so S-PBRR, crude and refined oil to biofuel conversion phase 1. Supercritical saltwater hydraulic injection with upcycled refurbished solar panels and artificial photosynthesis, AP panels via industrial symbiosis and e-waste as a resource input. So, in my design, the first industrial process to converting the refined or crude oil into ethanol, glucose, and hydrogen fuels is using a supercritical water reactor that I have a picture of here on the left that I just took from Google. The cool thing is about the newer generations of saltwater reactors. The last time I did a deep dive into researching saltwater reactors, I had seen some saltwater reactors, I believe in the US, that were already the size of small engines that could fit into a room, which before they were like massive, they were massive industrial machine sized machines. So it's cool now that they're becoming more smaller, modular, and more efficient because their saltwater reactors are quickly becoming a way to supercritical saltwater reactors. Are quickly becoming a way to process high energy materials. Supercritical saltwater, SCW, or sometimes supercritical saltwater SCW is created through an electrical generator or electrical coils powered by refurbished and upcycled solar panels via industrial symbiosis and or purchase of over sales of surplus of solar panels alongside potentially artificial photosynthetic or AP panels in later iterative editions of the S-PBRR or AP panels. Once artificial photosynthesis becomes more scalable on an industrial level. I'll try to sum this up without ranting on forever again. To my understanding, the most effective and efficient artificial photosynthetic systems are the bionic leaf systems being developed. The only two that I know of are one being developed in the US in Harvard recently, and the other in Italy. They show great promise as to outperform natural photosynthesis in the volume of glucose and carbon it can sequester, but I don't like to use the word sequester because it's associated with carbon sequestration, which is a stupid large-scale macro mechanical idea. I'd rather use the term artificial carbon cycling. But anyway, so yeah, the supercritical salt water basically mixes with the crude oil and begins to strip away a lot of its larger hydrocarbon chains. And if we're talking about supercritical salt water, the ionically charged minerals, the ionically charged sodium minerals, so the salt from the critical saltwater reactor, also have the potential to break down hydrocarbon chains and hydrocarbon bonds and further before it hits the first half of phase 2 of the process. But anyway, I'm going to continue. Sorry, I hope you understood that. Oh yes, and at the bottom left-hand side is a picture of a recycled or upcycled solar panel via industrial symbiosis. And if anyone has watched my previous lecture videos and 2 other videos, I'm a very big fan of industrial symbiosis that's being implemented institutionally on a large scale in Scandinavia, in South Korea, and a few other countries that I can't think of right now. That is showing great promise in resource sharing and between not just companies but between communities in refurbishing old electronics, in refurbishing old infrastructure, and also just as a way to not rely on the fragile supply chains and the just-in-time production vulnerabilities that I had mentioned earlier, and a great way to minimize e-waste accumulation as we are deciding to build more and more electronic systems. But anyway, I'm going to keep going before I run down forever. So I'm going to move on to part 1 of phase 2 because phase 2 is split into 2 halves. So the Symbiotic Photocatalytic Biofuel Reactor and Refinery crude and refined oil to biofuel conversion production phase 2 part 1. Photocatalytic and photonic reaction conversions from the refinery's walls and neighboring buildings and production facilities wall-mounted sun-reflecting mirrors, solar panels, and artificial photosynthesis arrays attached by heliotropic and digital digital and or analog programmed soft robotic mounted actuators. So what I mean by that is I envision the S-PBRR refinery as having biophilic outer walls for cooling the plant during the higher energy process of phase 2, part 1 and 2 of phase 2. And when I mean here about array of solar mirrors is I imagine really only having a few solar panels and just a few matrices of artificial photosynthetic panel arrays, so that by making large wall-mounted or vertical solar arrays on the walls and sides of neighboring buildings on the refinery's plant or complex, because refineries can have more than one buildings on its site. This not only optimizes solar energy in peak hours like Canada by using solar mirrors to reflect by using soft robotic actuator controlled heliotropic program soft robotic actuator controlled wall mounted solar mirrors, you could follow the sun as it moves through the day, and you could literally make up for the fractions of solar energy that you would lose as the sun moves further and further away from your facility, because the mirrors are programmed to follow the sun ideally at like a 360-degree angle. But yeah, those would be mounted on non-biophilic areas of the S-PBRR or S-PBRR complex's walls. And another industrial and manufacturing and ecological benefit to that approach is it doesn't require massive land sprawls for development for solar mirror enhanced solar panels like the ones in California or China, and I believe Australia as well. Anyway, on to the second half of that. So on the left-hand side, on the upper corner there, that's just a picture of a biophilic workplace. Obviously, there are benefits to biophilic workplaces having even miniature ecosystems, purifies air, which gives more oxygenation and is healthier for the brain of the workers, making them happier, more productive, more awake, makes them calmer, lowers their blood pressure, lowers exposure to green areas and aquatic areas, has been proven to lower stress levels. So that's really, and it would obviously increase productivity. But anyway, I'm going to just read the second paragraph here. So, before reaching the half-buried, half-exposed, locally produced biopolymer, which could be hemp, cornstarch, bamboo, etc., or glass silicate and or upcycled metal pipes that can't be retrofitted into biopolymer or glass silicate pipes, the supercritical saltwater mixed remaining hydrocarbon chains would then travel to a specialized area of piping protruding out right in front or above the semi-exposed or semi-buried pipes via indoor attached deep garden or sand beds. So what I mean by that is, before reaching an area of specialized pipes that would be buried either in a section of the floor that was removed so that they could be buried underground, or a large garden bed or a sand bed that could be brought into the plant so that these pipes could be buried, the top half of these translucent biopolymer and silicate pipes would be half exposed at the top to maximize the photocatalytic and the photonic solar charged energy coming in from both directions, which would further heat up and chemically break down any remaining hydrocarbons and molecule chains. Like I believe benzene is a big molecule chain in some oil and hydrocarbons. I believe, I could be wrong about that. Somebody correct me if I'm wrong. So yeah, it could break down stuff like benzenes. And then the reason why it's half buried underground and half exposed is that being half buried, it provides it with a natural passive thermal gradient that doesn't require any extra energy because it's cooler underground, and having it buried half underground would allow these pipes in phase 2 of the oil to biofuel and hydrogen fuel conversion to not heat up and crack so much under duress, especially given the perhaps more brittle nature of certain industrial biopolymer substrates, silicon glass and upcycled metal pipes. But anyway, protruding exposed transparent biopolymer / glass pipe section utilizing its transparent surface is heated up to several hundred degrees, further breaking down any hydrocarbon chains and or biological or chemical pollutants and contaminants. Then it is moved on to MFC scrubbing before phase 4 of the S-PBRR production cycle. I apologize there. That slide had a few errors I meant to correct, but I hope you got what I understood there. On the bottom left-hand side is a picture, if you can see, of a photonic laser. I don't know a lot about photonic lasers, but as far as I understand, some of them are directly powered by the sun or greatly assisted energetically by solar energy for power. So that's another advantage. Ideally, I would like to, in an experimental implementation, I would like to maybe start off with one or the other, maybe just having photonic lasers in the beginning, or photocatalytic semiconductors with photocatalytic lasers in the beginning. With one or the other in the beginning, just to see which one is actually more effective at breaking down any hydrocarbon chains and molecule groupings that are still left over. If it turns out that they are both scalable together and they can work in sync together, that would be awesome. And I didn't mention it up here, but ideally the photocatalytic and photonic lasers would also be powered by the extra solar energy captured by the solar mirrors, which would begin funneling them to the upcycled solar panels throughout the facility before the first phase of the production is even started. So I'm going to continue before I rant on forever. And sorry, and as always, if you find my voice annoying, just feel free to mute me and then just read the slides for yourself, even though it might be the odd error that I missed because I made most of this while I was super tired last night and the day before. Alright. So, S-PBRR crude to and refined oil to biofuel conversion production phase 2, part 2. So, I'm just going to move my recorder here. Of course it's got to do... No! Of course it's got to do this. Please bear with me a moment. Oh no. Okay, so you know what I'm gonna do? Bear with me, please. Alright, so anyway, so S-PBRR crude and refined oil to biofuel and hydrogen fuel conversion production phase 2 of 2 are to transparent biopolymers and or silicon glass pipes, base pipes or tubes, placed half exposed in the first half. Oh my god, another grammar error. In the first half of phase 2, funneling charged sunlight from the photocatalytic lasers, while the half or the glass while half of the glass or transparent polymer piping or tubes are buried several kilometers underground in the deep indoor garden or sand beds to utilize passive cooling as a thermal gradient, as well as an ideal environment to deal with increasing pressure of the oil to biofuel and hydrogen fuel conversion in the photocatalytic and photonic laser assisted enhanced reactions between the first and second stages of phase 2. Excuse me. So on the bottom there, sorry for that, just a few minor word errors that I thought I had corrected there. At the bottom is just a basic picture of a photocatalytic process on what I believe is another photocatalytic semiconductor or some kind of photoreactive surface, and it's just showing you a photocatalytic process. And here's just a picture I pulled off of Google of what looks like buried sewage pipes or water pipes, or maybe some type of high-speed internet pipes. I'm not sure. I can't really tell. The picture isn't the clearest. But anyway, that was phase 2 of the crude and refined oil to biofuel and hydrogen fuel production, phase 2. As I mentioned, there are 2 stages to phase 2, and that was the second stage of phase 2. And this is stage 1 of phase 2, if you want to go back and watch it. So moving on, powering through. So, S-PBRR, crude and refined oil to biofuel and hydrogen fuel conversion production phase 3. The Symbionic UENP methodology for cycling of the remaining chemical waste of the... Hold on. I love how I can never move any of these recorders and Loom when I'm not recording. Oh, there we go. So I'll start that over again. S-PBRR, crude and refined oil to biofuel and hydrogen fuel conversion production phase 3. The Symbionic UENP method for cycling of the remaining chemical waste of the soil to biofuel conversion production process and microbial fuel cells. Phase 3 is where the remaining carbon residue and unwanted and unintended chemical bonds from any crude or refined oil/gas is finally moved through the implementation of microbial fuel cell units, or MFCs, or large bioreactors made from converted or retrofitted oil drums, where any remaining organic toxic sludge from the oil to biofuel conversion production phase process is consumed and converted into fuel for electrical current via microbial fuel cells, or my own design for what I call, not when I call, the Symbionic eco-industrial cellular membrane. There, yeah. So, as I said, there are a few word typos because I wanted to make this as quickly as I could, given the accelerating global events around the world and the accelerating events of the U.S.-Israeli war in Iran and the economic fallout it's having on sustainability and biomimicry. Anyway, I'll get more into my design of the SEICM later in another lecture video. I don't really have the time I would want to fully get into a Symbionic eco-industrial cellular membrane and how it's kind of a, not to brag, but an already superior design methodology for microbial fuel cells. So right here is a picture of an excuse me. Right here is a picture of an oil drum or oil container. The reason that they would be ideal units for macro microbial fuel cells, or my macro Symbionic eco-industrial cellular membranes, or a bioreactor, is that the material for oil drums, which I believe is like aluminum and probably some other stuff, is pretty well suited for anti-corrosion in the short to midterm. And if you were to put a plate in the middle of an oil drum, you could have a situation where you could have two separate microecologies in the same microbial fuel cell or bioreactor. I'll get more into that later, because that essentially goes into my Symbionic eco-industrial cellular membrane design. And over here is a picture of a bioreactor that I pulled from Google, and over here is a picture of a basic microbial fuel cell diagram. Oh, and right here, speak of the innovative devil. This is a diagram I made based off of my written schematic with AI of an eco-industrial cellular membrane, which I will make another lecture video on someday. Yeah, that's another piece of technology that will make Symbionics, or urban ecological niche prosthetics, more scalable in the mid to long term and even short term. But I'm going to continue. So, the net positive energy gain of the S-PBRR. 1. Surplus hydrogen fuel production through catalytic water splitting in phase 1. Surplus glucose ethanol biofuels production from artificial AP bionic leaf arrays and natural wall-mounted gardens and biophilic interior and exterior of the S-PBRR. 3. Surplus of added energy storage in the form of microbial fuel cells from phases 3 to 4, and surpluses of bioreactors and potentially Symbionic eco-industrial cellular membranes. So what I mean here is to say that if my current design for the Symbionic Photocatalytic biofuel reactor and refinery works even 40%, 50%, or 40%, or even less, I guarantee you, is going to have a net surplus of biofuel, at least one of the biofuels mentioned, and at least hydrogen fuel for sure, because that is a chemical reaction, a natural chemical byproduct of using artificial photosynthesis and photocatalysts in the same system. So over on the left-hand side, you have a diagram of a hydrogen fuel cell, and obviously, hydrogen fuel could easily be made with artificial photosynthesis. On the right-hand side here is a diagram of an ethanol fuel cell, and in the middle is another different schematic representation of my eco-industrial cellular membrane. Excuse me. Jeez, try saying that 10 times fast. Eco-industrial cellular membrane. Eco-industrial cellular membrane. Eco-industrial cellular membrane. It's hard. Anyway, so yeah, literally. So the S-PBRR would not only be creating the surplus ethanol biofuel, would not only be creating the would not only be creating ethanol biofuel, glucose biofuel, and hydrogen fuel from the conversion of the oil, from the conversion of the crude and processed oil and gas. It could also create a surplus of those fuels because of the integration of microbial fuel cells in the final polishing in phase 3, and the economic viability of my Symbionic eco-industrial cellular membrane design that is essentially a multi-microbial ecosystem microbial fuel cell designed via microbial catalyst hinges to connect with each other to scale up and produce higher voltages of energy for future symbiotic technologies. But anyway, I'm going to keep going. So yeah, so not only would you have the energy in the form of the biofuels that you had converted from the oil or gas, you would also have potentially, if it works 100% or even 50 to 40% as designed, you would have three kinds of energy. You'd have three forms of surplus net energy. You would have extra hydrogen fuel from the photocatalytic splitting of water and the hydrocarbons. And you would have a surplus in ethanol and glucose biofuels just from the artificial photosynthetic matrices. And you would have a surplus of solar energy being collected even before the industrial oil to biofuel and hydrogen fuel production phase begins. So, yeah. So instead of gouging out large sums of money to rescue what little dwindling oil supplies we have left, either in the form of stranded oil assets that are sitting idle now in national reserve storage units, or literally off the coasts of ports because of the energy crisis in oil tankers. You could actually, instead of doing that, you could literally gain three forms of extra surplus of energy just from converting the oil and gas to biofuels and hydrogen fuels, that you could then turn around and use those net gain hydrogen and biofuels and microbial fuel cells and potentially SEICMs to power the S-PBRR in later iterative designs and fully functioning plants. So it's literally creating further energy sovereignty for my design. So by creating a net gain of extra surplus energy, it could be put back into the very process that creates the energy that you want to create in the first place. So you're literally getting way more bang for your buck than you would get trying to treat oil or drill in deep oil wells that are dwindling anyway. And as I'll get to in a minute, the return on investment for fracking and shale and digging in the deepest oil wells and the deepest oil wells possible, like the Alberta oil sands and even the so-called future Saskatchewan oil sands, aren't even going to be economically viable because it costs more to get the oil out than they'll actually get in overall revenue. So anyway, I'll get to that later. So, what are the economic and scientific benefits of developing an S-PBRR? So on the left-hand side is a AI-generated image based off of a detailed schematic I wrote in design, S-PBRR. It breaks down the phases, but it kind of hallucinated some of the words. But you don't really have to focus on that. Just kind of the look and the layout of it is generally correct. Although, as I always say, my AI schematics are not meant to be literal representations of what the physical blueprint would actually look like. They are just visual learning aids to help you understand kind of what I'm going for. For those of you familiar with any chemistry history, any alchemy or occult history, that there is the symbol of the Ouroboros and the hydrocarbon. And no matter how high profitability oil is, given it's in the lifeblood of industrial economies, it will ultimately eat itself. And I think the Ouroboros is the perfect symbol for the dying petrol age, because we're running out of oil. We've kind of known that since the 70s. Peak oil really hasn't gone away. As I said, shale is called the shale paradox because they're spending way more money than they get out of revenue from retrieving these deep underground oil wells and oil sands, because it's literally so energy and economic and mechanically intensive. At the bottom here is a picture of a Thai ship, a Thai cargo ship, I believe, because it says Bangkok, burning because it was struck during the conflict around the Strait of Hormuz. It's like the ultimate symbol of our age and the death of sustainability and biomimicry. That's why I used it in my 11-minute rant about why the U.S.-Israeli war in Iran and the Strait of Hormuz energy crisis is going to be and is the ultimate death of sustainability and biomimicry, because they didn't invest or even try to really find any alternative liquid-based fuel to have as a backup before trying to scale up solar energy, wind energy, tidal energy, geothermal energy, or the like, which I think is a major blind spot on their behalf, because by relying on a cleaner liquid fuel instead of other energy sources, you don't have to tear everything up and start over. You can literally just retrofit existing gas and oil and energy production sites and facilities that are already built to withstand high pressure and high energy and chemical reactions to convert oil into gas and oil into diesel. So it's not really that it's not really that fanciful. It's not really that far-flung an idea or radical of an idea even to retrofit all existing oil infrastructure and gas infrastructure into biofuel and bioreactor production facilities, because they're literally the ideal place to start building them. And if you've been watching my channel before and any of my previous 6 lecture videos and my PhD paper reading, you know that I'm a huge fan of instead of starting from scratch, which isn't economically or environmentally or ecologically viable, retrofitting is a far more viable and attractive model for I call it just the reindustrialization of post-industrialized so-called capitalist economies, but the eco-industrialization of industrial capitalist economies. But I'm going to continue. So, before I just go on to the other scientific, engineering, and economic benefits of an S-PBRR, here is a schematic visual representation of finalized design of my S-PBRR. Yep. So, like I had said here, this is the upcycled solar panel starting the critical saltwater reaction. These are the artificial photosynthetic and biophilic matrix on the walls of the refinery and neighboring buildings. This is supposed to be representing inside of refinery, but type of natural and artificial photosynthetic biophilic matrix or interior. Type of. Let me start over. This type of natural and artificial photosynthetic combination matrix is suitable for both inside of the S-PBRR to treat any any chemical or gas leakages that come in from outside of the building and purify the air and detoxify the air before it reaches the wider outside, but also inside of the building because of workers inside of this S-PBRR could be potentially exposed to toxic fumes from the conversion, the oil to biofuel and hydrogen fuel conversion. So lining the walls with air scrubbing plants and vines and even moss, grass, and potentially algae could not only purify the air for them, but also, which would make it better for them to breathe, but also minimize the chances of any toxic leaks into the plant itself, because a lot of biophilic and wall gardens are being used as bioremediation. And if you look at the phase 4 net regenerative sink phase on this schematic, you can't really tell all too well because it's all kind of crammed together, but this section here is representative of the indoor and outdoor urban agricultural gardens that would be used to feed the force of the S-PBRR, give them a natural and organic healthy source of food for their day, but also the waste from the food could be turned into nutrient recovery for the soil, nitrogen recovery for the surrounding soil, and oxygen recovery for the surrounding air and soil. As you know, if you're familiar with my previous lecture videos, all of my buildings rely on the central concept of artificial biogeochemical cycles connecting to natural biogeochemical cycles with soft robotic skeletons. That means to generate the air, water, and soil and ecosystems and biodiversity. The S-PBRR is no exception. It is a symbiotic building with artificial natural biogeochemical cycles that would regenerate its surrounding air, water, and soil, flora and fauna, and create a conducive environment for even wildlife to live in a symbiotic urban environment like this. Anyway, so that is a visual representation there of my S-PBRR. Again, it's not a perfect blueprint, actionable blueprint that I'm going to physically design a real S-PBRR on, but I will. It is a good tool and learning aid to help you kind of understand. And if you look over here, this is polycultural crop management. I'll get to that more later, but I've designed a methodology for the S-PBRR land management where all biofuel crops will be managed through the use of polyculture and intentional natural ecosystem pressures to create more healthy and genetically diverse biofuel crops that don't degrade the soil. Anyway, but I'll get on to the topic of this specific slide before I rant on forever. So there are not only huge scientific benefits, e.g., restoring natural biogeochemical cycles and life on the earth for converting oil into biofuel and hydrogen fuels and getting us off the fuel that's literally killing our planet and us. But there's also thermodynamic, thermodynamic and scientific imperatives that almost make my S-PBRR design more viable than trying to rescue and convert the remaining stranded oil assets or idle oil assets being caused by this oil energy shock. And I can prove it just by listing just 6 problems that come with leaving oil idle for too long, whether it's crude or it's processed and refined. And it's funny, I was trying to find a way to put all of the problems that you run into when oil is left idle, whether it's again crude or fully refined. But there's so many that I couldn't fit them all on 2 or 3 slides, so I had to just pick a few main problems to go with long-term oil. So one main thermodynamic problem with oil and oil infrastructure storage and management long term, especially in situations like the Strait of Hormuz energy crisis, where there are huge supplies of oil being stranded and idle right now, is that they are susceptible to aerobic and anaerobic microbiological fouling and degradation. So microorganisms get in there and eat the hydrocarbons or break the hydrocarbon chains. Photooxidization and free oxidization reactions. So if any free oxygen gets in through like a crack in the container or micro cracks or micro holes in an oil drum or any type of oil containment facility or container, oxygen could bond with some of the molecules inside of the hydrocarbons, depending on the amount of oxygen coming into the hydrocarbon pool or the hydrocarbons being stored. Those are just 2 forms of natural weathering oxidization problems that face long-term oil maintenance and storage management. Pit formation. Now, anybody in the comments section, feel free to correct me on this because I don't really know a lot about pit formation in oil degradation, but I think pit formation refers to specific pockets or zones where microorganisms or a combination of water and air pockets or both can form and create almost like little pockets of biomineralized areas of the soil, like almost like a granite-like substance. I think. Feel free to correct me on the section because I'm not 100% sure on what exactly pit formation is, even though I did quickly look it up. But I do believe it refers to when microorganisms, whether aerobic or anaerobic, find their way into oil container or oil or gas facility and create localized pockets of air and water that there's a level of moisture and air that creates conditions for those same microbiological organisms I mentioned to accelerate the fouling of the oil. And also, along with pit formation, that might not compromise all the oil, but some of the oil, which would require to be chemically treated, which is more energy and more money down the drain. Also, organic acid formation. Yeah, a lot of microorganisms that feed on petrochemicals can produce organic acids as a byproduct and further contaminates the oil. It could also be carbonic acids, but I'm not quite sure about that. I'd have to go back and look that up. And I'm currently reading William C. Schlesinger's biogeochemistry, so I'll have to go back and look it up. But yeah. So those are just those are just 3 examples of the things that can go wrong with storing oil and gas long term when it's left idle and not being used. Like, it literally costs so much just to keep oil infrastructure in place. It's absurd. I'm going to keep going. So I'll give you two examples. Especially as of 2026, the ROI on treating chemically or biologically compromised or contaminated of stored crude or refined oil easily exceeds the revenue gained on the international oil market. For example, a study I believe done between 2024 and 2023 in British Columbia, Canada, that used fisheries to treat an oil spill so that they could recover some of the oil to sell it back to the oil company. It cost them roughly $2.4 billion to treat the oil and remove its contaminants with fisheries, while the oil company only gained a relatively meager profit revenue return of 180 million CAD or US dollars. So again, to somebody like me, $180 million is amazing, baby. Like, I could build a whole new laboratory and a whole new life and get all my inventions off with $180 million. But to a major multi-billion-dollar oil company, $180 million for a $2.4 billion oil treatment recovery process is absurd. You're literally bleeding money through your pockets. Like, it's absurd. And although I couldn't fit the information down here, this is a link to a 2024 study on the International Oil Cleanup Spill Conference of 2024 in London, England. If I just move my head out of the way, literally. Let me just. What? Oops, one sec. Let me just move my head out of the way if I can. So down here, the financial cost of oil spills, TOPF 2024. Feel free to copy that link or type in that link, that URL. That international study from 2024 definitively proves that the return on investment for trying to recover chemically contaminated, corroded, or biologically contaminated or corroded oil does easily. The overall cost of treating biologically or chemically contaminated or compromised oil easily exceeds any return on investment or revenue gained from actually treating said oil. So another effect of what I call the petrol-Ouroboros effect. And on the left-hand side is another visual schematic of the S-PBRR or Symbionic Photocatalytic Biofuel Reactor Refinery. So again, please feel free to look into that study in British Columbia. Don't just take my word for it. These are actual data points that I used. And please feel free to copy that URL or type that URL and read that whole PDF, because that international study from 2024, only 2 years ago, before the energy crisis, definitively proves that the cost of trying to retrieve and treat oil is not even profitable for the amount that it costs to do so. But I'm going to rant on forever. So, prototyping, retrofitting, and constructing the first S-PBRRs using Symbionic UENP, Symbionic Building Envelope Retrofitting Methodology, or S-PBRR methodology. For those of you who have seen my PhD prospectus reading on symbiotic sphere theory, engineering planetary symbiosis with the biosphere. Here, again, this is just an AI schematic based off of my written schematic as a learning aid and visual aid to help you understand. These spiraling structures, I don't know why I generated them. I think it just, maybe it saw them as it hallucinated that they were energy efficient or somehow mechanically efficient. But I do like them but I do like the spiral look aesthetically. But obviously, this is just a sort of obviously just a horizontal basic layout of each phase to show you what it would sort of look like and S-PBRR would look like inside. So I'm going to keep going. So, as I mentioned previously, I'm a huge fan of retrofitting already existing buildings and infrastructure rather than starting from scratch because that's far more economically viable, cheaper, and not dependent on globalized supply chains and just-in-time production. And what better way, and what better structure to start retrofitting and building an S-PBRR than an already existing, damaged oil refinery. On the left-hand side is a picture of a damaged Russian oil refinery from a Ukrainian oil strike, and on the right-hand side is a picture of a damaged Saudi Arabian oil refinery from an Iranian drone strike. So it doesn't matter what geopolitical side you're on in the battle between the Chinese-led BRICS or the U.S. dying G7. Your energy oil infrastructure is going to be targeted whoever side you're on. So yeah, and these are all recent conflicts. These are not from the 90s. These are all from the 2020s. So keep that in mind. So I can already see a lot of Canadian and American and Northern European audiences rolling their eyes at my entire lecture video, being like, this is a great idea when there's solar energy optimization for peak hours. It would never work in the wintertime. Well, I'm way ahead of you there. So this is prototyping, retrofitting, constructing the first S-PBRs using Symbionic ENP SBR methodology. What about in northern winter climates like Canada, Norway, Russia, or Alaska, USA, etc.? Well, on the left-hand side is just a picture of a Canadian or Russian oil refinery in the winter. And right here, if I can just move my fat head, is a picture of the winter variant of the S-PBRR. It's contained within a inflatable or deconstructible geodesic biodome, which would make it ideal because geodesic biodomes are already proven structures that are resilient to high gusts of wind. And in the winter, when solar energy is no longer optimal and solar energy can't be utilized for outside artificial photosynthesis, during the spring and summer months, I envision that the S-PBRR facility staff and scientists and engineers would create a seed bank of ethanol and those biofuel crops to storing during the spring and summer months so that they could put them in greenhouses built on the S-PBRR. Excuse me one sec. Built on the S-PBRR facility. Excuse me. And so that they could switch the biofuel crop growing to greenhouses and indoor vertical gardens of the refinery itself. Yeah, and also they could switch the artificial photosynthetic production to greenhouses and the geodesic or domes as well, and that keeps going through the winter, and those greenhouses and geodesic domes in turn would be powered by the surplus glucose, ethanol, and hydrogen fuels that would be produced over the spring, summer, and early fall months. So yeah, here's a closer look of the S-PBRR winter variant. So again, it's powered by agricultural sink from the urban agricultural indoor and outdoor gardens as a resource fuel stock. It's also powered so the greenhouses, the geodesic biodome could be powered by the already produced and stored surplus ethanol biofuels, glucose biofuels, and hydrogen biofuels, as well as the indoor artificial photosynthetic and natural biophilic matrices that would be switched to inside the plant or inside the greenhouses or geodesic domes or domes. And again, geodesic domes are already proven to provide great insulation for semi-closed ecosystems. And I would just like to mention that my designs are nothing like the Biosphere 2 experiments in Arizona in the 1990s. I explicitly design all my systems as semi-closed or controlled open systems, just like cell membranes, so that the system can allow itself to bring in new materials in the form of energy, matter, and information. E.g., my central equation, continually repair itself and expel out any waste produced that could be put back into the environment, just like a cell. But yeah, I'm gonna keep going. So hopefully you understood my giant rant about the winter variant of the S-PBRR and how by switching to glucose, ethanol, and hydrogen fuel powered and indoor AP powered domes and greenhouses, the S-PBRR would still be able to produce and convert oil into biofuels and hydrogen fuel even in the winter times in places like Canada, Norway, Sweden, Finland, Russia, and maybe even in an Arctic and Antarctic station. So I'm going to continue. So the winter variant of the S-PBR design logic. Wow, I just realized I just said the whole slide that I just wrote here. But anyway, energy resistance and resilience during solar deprived seasons through stored microbial fuel cells, symbiotic eco-industrial cellular membranes, stored glucose, ethanol, biofuels, and hydrogen fuels to use during winter and fall months, utilizes biofuel crop seed banks stored during spring and summer seasons to move biofuel crop cultivation to neighboring or on-site greenhouses and biodomes, utilizes partially or fully buried pipes tubes to maintain a constant thermal gradient in underground spaces, like a partially integrated SSREN or Symbionic subterranean re-earthing network, or Symbionic artificial metal and sediment cycle. Unfortunately, I do not have the time or space on this lecture to get into the Symbionic artificial metal and sediment cycling system, but that's evidence that I'm thinking further ahead than most sustainability and biomimicry experts and generative architecture design experts, because none of them are thinking about the lithosphere or the current cycle or the sediment cycle. So I'm the only Symbionics or UENP is the only framework actually accounting for the lithospheric generation and sediment cycle generation, which is essential for soil regeneration. If you watch my previous lecture on urban ecological niche bionics, transforming architecture through urban agriculture or something, before I had switched the acronym to urban ecological niche prosthetics for more accuracy, I explained what the SSREN is and how that even before I want to build a full-scale symbiotic subterranean re-earthing network, it would be ideal to start experimenting in shaping SSRENs in underground parking lots, underground sections of buildings attached to already existing buildings, or symbiotic UENP buildings above ground, just to see what the viability long-term of an SSREN would be for arc against high house Earth for biodiversity and human protection. So anyway, utilizes fully partially buried. Oh yeah, I already said that. Like a partial SSREN or the SAMSC facility, or the resource cycling in phase 4 via urban gardens and biophilic interior walls, interior walls encased in an inflatable or di- di- disassemb- dis- disassemb- 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 Jesus Christ, disassemblable geodesic dome for weathering shelter. All right, so biofuel crop land management for an S-PBRR. So polyculture-based agriculture production in order to increase genetic diversity. One second here. I always do this to myself. For genetic diversity of the biofuel crops in question, while also eliminating the potential for nutrient gradient. It says radiant, but I meant to type gradient. Nutrient gradient competition among crops of the same or different species, alongside growing multiple biofuel crops together with enough natural plants and foliage and shrubs and or bushes as buffer green spaces in between each biofuel growing crop section or plot. So I imagine, so on the left-hand side is a representation. On the left-hand side is a representation of polyculture agriculture and how it's far more regenerative and easier on the soil than large-scale industrial monoculture, because it actually renitrifies the soil and encourages more soil microecosystem biodiversity and doesn't create large amounts of nutrient runoff like a large-scale industrial monoculture. And I envision having all the biofuel crops grown together, whether corn, bamboo, any other starch biofuel crop, but separated by ferns, bushes, pollinator plants, so that they don't end up competing with each other, or there's a lower risk of them competing for each other with nutrients. But also making sure that the soil itself is regenerated with the very process of cultivating and producing these biofuel crops, and doesn't actually degrade the soil, because what would be the point of Symbionics if my biofuel crop management methodology for the S-PBRR degraded the soil just the same as industrial monoculture. The introduction of natural or artificial man-made wetlands and ponds, and earthworm and aquatic earthworms buried or semi-buried in the soil. Sorry, I'm just going to move my fat head again. Wetlands, ponds, earthworm farms buried and semi-buried in the soils, and aquatic worm farms buried and semi-buried in the soils. The earthworm and aquatic earthworm farms. No, Jesus. I always do this to myself. Also act to replenish the nutrients in the deeper layers of the soil and produce necessary porous clays like humus clays that are necessary for long-term lithospheric health and nitrogen cycling of the soil. Tree farms and nurseries around the lawns and tree farms and nurseries around the lawns and perimeters of the refinery and neighboring buildings act as a form of phytoremediation and bioremediation. And mycelium networks would also be planted deep in the soil of the tree farms and nurseries to also act as a form of bioremediation, because mycelium, fungus, and mycelial networks and fungi are well known to detoxify the soil from heavy metals and chemicals. So they would be a great biological line of defense for the S-PBRR if something biological or chemical leaked outside. And here's another picture of polyculture crop management on an indoor farm facility. The thing I didn't mention here that I wanted to is that another benefit potentially of the S-PBRR is that just as oil refineries and large-scale oil allowed us to create building materials like plastic and allowed us to scale up our fertilizer production, I actually would argue that my S-PBRR has the great potential for creating high yields of organic fertilizer, the biofuels and hydrogen fuels that are created, like industrial fertilizers that are now being affected by the Strait of Hormuz energy crisis, such as those high in phosphorus and phosphates being affected. There's obviously an imperative to already start switching to an organic fertilizer alternative to industrial fertilizer. I think that the biofuels created by my S-PBR design and the S-PBR's natural phytoremediation and bioremediation capabilities and biogeochemical restoration capabilities make the potential for the S-PBRR and its biofuels to create large amounts of organic fertilizer quickly that would not only help produce healthier plants for human and animal consumption, but also help to reduce the soil, also help to regenerate the soil and soil microecosystems itself. And also the worms, the earthworm and aquatic worms buried underground in ponds beneath the surface would also act as a form of bioremediation because they too can absorb things like heavy amounts of radiation, toxic metals, and chemicals. So, conclusion: the S-PBRR, even in this design phase, proves that Symbionics, or urban ecological niche prosthetics (UENP), is a vastly superior scientific engineering and far more economically viable emergency infrastructure framework and methodology for not only scaling up and maintaining a mass level of high quality, ready production of multi-biofuel crops as a rival to electric vehicle production. Such a symbiotic or S-PBRR energy system would also primarily actively help to ecologically regenerate biogeochemistry than to degrade it. 1 second here. Move my fat head again. The S-PB... I hate when it shows the taskbar. It looks so tacky. The S-PBRR is not only far more economically viable path for using stranded and idle oil reserves than trying to chemically and biologically treat them back into their hydrocarbon Ouroboros complex, destined to implode sooner or later. Finally, and most importantly, it proves that unlike traditional biomimicry and sustainability, Symbionics, or UENP, is the only path toward energy sovereignty away from the petrol sustainability paradox or lock-in. In other words, Symbionics UENP, or urban ecological niche prosthetics, is the only framework that doesn't require any oil to start up, any new oil infrastructure to start the engine. Symbionics UENP is the only framework that doesn't require any oil to start the scale-up engine for civilizational eco-industrialization. Hopefully you understood that. And again, if you find my voice annoying, just mute the videos and work your way through the slides on your own. I apologize for the few minor typos there in the first 2 slides that messed me up. So in conclusion, move my fat head again. So in conclusion, it's either, if you're a person who is passionate about eco-technology and eco-architecture, whether on land or in the ocean, this energy crisis caused by the U.S.-Israeli war in Iran and the fallout of the Strait of Hormuz closure and energy shock and crisis is going to cause people in the green tech and architecture sectors to have to choose between trying to maintain a sinking ship, literally, and on a sinking ship that's going to exhaust itself out anyway because we're running out of deep oil wells and it's no longer economically viable to even try to retrieve those deep oil wells or fracking or shale, e.g. the shale paradox, look that up too. And yeah, so you can either spend all that money trying to chemically, and you can spend all that money trying to oil to get rid of all the biological and chemical contamination and degradation that happens from it just sitting idle, which will cost you way more money than you'll get out of putting it back into the market, or you can convert it into a photocatalytic biofuel and refinery and create not only glucose fuel and hydrogen fuel, but a surplus of glucose fuel, glucose biofuel, ethanol biofuel, hydrogen fuel, and microbial fuel cells that will produce an electrical charge from the stage 3 of the final of the fuel, and potentially even my Symbionic eco-industrial cellular membrane. So yeah, you literally have 3 forms of extra surplus of energy just from my design alone, even if it works 40 to 50% as designed. So yeah, you're getting far more bang for your buck if you're thinking like a capitalist, but I'm not. So that's why I'm winning, and sustainability and biomimicry are dying. So thank you anyone watching. This has been me trying to power as much as I can through this really complex lecture video. It's really hard for me to really complicated invention like the S-PBRR and its industrial processes into a digestible slideshow. But I've hoped you've understood the entire presentation. And if you have any questions, please feel free to comments below, and please like and subscribe, obviously. And also, to any naysayers out there who might be in the sustainability and biomimicry industries who like to say it will never happen, by all means, tell me why none of my inventions will never happen. I would love to hear you to me scientifically, engineering, and economically why none of my inventions will never happen, and what is scientifically or engineeringly unviable about them. I love to hear your criticisms and feedback, because I guarantee you none of you have thought of a viable way to get us off of fossil fuels the way I have. So further proof that I'm running circles around sustainability and biomimicry with just a laptop, my smartphone, limited programming skills, and my imagination, outperforming multi-billion-dollar sustainability, clean energy, and biomimicry labs. So okay, thank you everyone. This has been Engineering Symbiosis AD. Have a great night, everyone. Bye.